Welcome back, aspiring cybersecurity professionals, to episode 6 of our comprehensive cybersecurity course. I'm your instructor, and I'm thrilled to continue this journey with you. In our previous episodes, we established a strong foundation, diving into the core principles of cybersecurity, understanding the threat landscape, and exploring essential concepts like networking fundamentals and cryptography. We've built a mental framework for how digital systems interact and what vulnerabilities they often present. Today, we're shifting our focus to a critical component of virtually every digital ecosystem, and an absolute cornerstone for anyone serious about a career in cybersecurity, the operating system. Specifically, we'll be embarking on our journey into the world of Linux. This episode, titled Linux for Cybersecurity, Complete Basics, is your gateway to understanding why Linux isn't just another operating system, but a powerful ally and an indispensable tool for every cybersecurity practitioner, whether you're a hacker, a defender, or an analyst. By the end of this session, you'll grasp the fundamental concepts and commands that will empower you to navigate, understand, and secure Linux environments effectively. So, let's dive in and unlock the power of Linux. Before we delve specifically into Linux, let's briefly contextualize the operating system's role in the cybersecurity landscape. An operating system, or OS, is essentially the master program that manages all other applications and hardware on a computer. It's the central nervous system, providing the interface between the user, the software, and the physical machine. From a cybersecurity perspective, the OS is a prime target for attackers because compromising it often grants deep access to the entire system, all its data, all its applications, and all its resources. Think of it like the main entrance to a building. Secure the entrance, and you've secured a major point of vulnerability. Conversely, if an attacker bypasses that entrance, they essentially have free rein. Understanding how different operating systems work, how they're structured, and how they manage security is absolutely fundamental. While Windows and Mac OS dominate the desktop market, it's a different story when we talk about servers, embedded systems, and especially, cybersecurity tooling. In these critical areas, one operating system stands head and shoulders above the rest: Linux. Its ubiquity, flexibility, and robust nature make it a critical skill set for any cybersecurity professional, which is precisely why we're dedicating an entire episode to its fundamentals today. So, why is Linux considered the undisputed champion for cybersecurity? It boils down to several key advantages that make it indispensable. First and foremost is its open-source nature. Unlike proprietary operating systems, Linux's source code is freely available for anyone to view, modify, and distribute. This transparency is a massive security benefit. A global community of developers constantly scrutinizes the code for vulnerabilities, bugs, and backdoors. This collective auditing leads to faster identification and patching of security flaws, making it inherently more robust. Second, flexibility and customization. Linux is incredibly modular. You can strip it down to a bare-bones system for maximum efficiency and security, or load it up with specialized tools. This allows cybersecurity professionals to tailor their environments precisely for specific tasks, whether it's penetration testing, forensic analysis, or securing a server. Third, stability and reliability. Linux-based systems are renowned for their uptime and stability. Servers often run for years without needing a reboot, which is crucial for critical infrastructure and long-term security monitoring. Fourth, a plethora of cybersecurity tools. The vast majority of leading open-source cybersecurity tools, from network scanners like nmap and vulnerability analyzers like Nessus, to exploit frameworks like Metasploit and forensic utilities, are either developed primarily for Linux or function best within a Linux environment. It's the native habitat for these powerful instruments. Finally, the command line interface, CLI. While graphical interfaces are convenient, the Linux CLI offers unparalleled power, precision, and automation capabilities. For complex tasks, scripting, and remote management, the command line is far superior, enabling advanced operations that are often difficult or impossible with a GUI. These factors combined make Linux not just a preference, but a fundamental requirement for anyone operating in the cybersecurity domain. When we talk about Linux, it's not a single operating system, but rather a family of open-source Unix-like operating systems based on the Linux kernel. These variations are called distributions, or distros, and each is tailored for different purposes. Let's look at 3 prominent ones relevant to cybersecurity. First, we have Kali Linux. This is arguably the most famous penetration testing and ethical hacking distribution. Developed by Offensive Security, Kali comes preloaded with hundreds of tools, organized into categories like information gathering, vulnerability analysis, web application analysis, password attacks, and more. It's built on Debian and optimized for security tasks, making it a go-to for penetration testers and security researchers. Second, there's Parrot Security OS. Also designed for security professionals, Parrot OS offers a similar suite of tools to Kali, but it emphasizes cloud friendliness, anonymity, and forensics. It often includes tools for cryptography, privacy, and digital forensics right out of the box, and aims for a lighter footprint and more user-friendly interface than Kali, while still being extremely powerful. Finally, Ubuntu. While not specifically a cybersecurity distribution like Kali or Parrot, Ubuntu is one of the most popular and user-friendly Linux distributions overall. It's widely used for general computing, server deployment, and development. Its importance in cybersecurity stems from its widespread adoption as a server OS, meaning security professionals often need to secure, manage, or analyze Ubuntu-based systems. Furthermore, its extensive software repositories make it easy to install many cybersecurity tools, making it a perfectly capable platform for security tasks once configured. Understanding these distributions helps you choose the right tool for the right job, whether you're performing an offensive security operation or defending a critical server. Now that we understand why Linux is so crucial and have met some of its key distributions, it's time to get our hands dirty with its most powerful feature, the Command Line Interface, or CLI. For many newcomers, the terminal can seem intimidating, a black box filled with cryptic commands. But I assure you, it is your greatest ally in cybersecurity. The CLI grants you direct, granular control over the operating system, allowing you to perform tasks with precision, speed, and automation that simply aren't possible with a graphical user interface. This is where the real power of Linux is unleashed. For hackers, both ethical and malicious, and for defenders, mastering the command line is non-negotiable. It's how you navigate file systems, execute tools, analyze logs, manage processes, and ultimately, understand the underlying workings of a system. We're going to start with the most essential commands, the building blocks that will allow you to interact with any Linux system effectively. Think of these as your basic vocabulary in the language of Linux. We'll break them down into categories to make them easier to digest, starting with navigation and information gathering. Remember, practice is key here. The more you use these commands, the more natural they will become. Let's begin our command line journey with navigation and basic information gathering. These commands help you find out where you are, what's around you, and how things work. 1. pwd, print working directory. This simple command tells you your current location within the file system hierarchy. It's like asking, where am I, in the digital world? For instance, typing pwd might return /home/kali/documents, indicating your current folder. 2. ls, list directory contents. This command lists the files and directories in your current location. ls will show a basic list. ls-l provides a long list format, showing detailed information like permissions, owner, group, size, and modification date. This is incredibly useful for security analysis. ls reveals all files, including hidden ones, those starting with a dot, like .bash. Attackers often hide malicious scripts or configuration files this way. 3. cd, change directory. This is how you move between directories. cd/etc takes you to the /etc directory, which holds system configuration files. cd moves you up one level in the directory hierarchy. cd, or just cd, takes you to your home directory. cd takes you to the previous directory you were in. 4. Manual. The man command is your built-in help guide for almost any command. If you forget what ls does or want to know its options, simply type man ls, and a detailed manual page will appear. This is an invaluable resource for learning and troubleshooting. 5. History. This command displays a list of previously executed commands in your current shell session. For a defender, analyzing the history file of a compromised user can reveal attacker actions. For an attacker, it's a way to recall useful commands or clean up their tracks. Mastering these few commands will give you immediate confidence and control in the Linux terminal, allowing you to begin exploring any system you encounter. Beyond just navigating, you'll constantly need to interact with files and directories themselves. These commands are your fundamental tools for creating, copying, moving, deleting, and examining file content. 1. Dir, make directory. This command creates a new directory. For example, dir my_project will create a directory named my_project in your current location. 2. Cp, copy, used to copy files or directories. Cp source.txt destination.txt copies a file. Cp, our directory 1 directory 2 recursively copies an entire directory and its contents. Be cautious with cp as it can overwrite files without warning if permissions allow. 3. mv, move/rename. This command moves files or directories from one location to another, or renames them. mv file.txt new_location /moves file.txt to new_location. mv old_name.txt new_name.txt renames old_name.txt to new_name.txt. Attackers often use mv to relocate tools or disguise malicious files. 4. rm, remove, used to delete files or directories. This command is powerful and irreversible, so use it with extreme caution. rm file.txt deletes file.txt. rm, our directory_name recursively deletes a directory and all its contents. There is no recycle bin in the Linux CLI for rm. rf directory_name is the most dangerous form, R for recursive, F for force, meaning it will delete without prompting. Never use this casually. 5. Cat, concatenate and displays the entire content of a file to the terminal. cat/etc/password will show the contents of the password file, a common target for initial reconnaissance. 6. Less, for viewing large files, cat isn't ideal as it scrolls past too quickly. Less allows you to view file content page by page, scroll up/down, and search within the file. It's crucial for examining long log files or configuration files. 7. grep, global regular expression print. This powerful command searches for patterns, text strings, within files. grep root/etc/password will display only the lines in /etc/password that contain the word root. This is incredibly useful for filtering logs, finding specific configurations, or identifying malicious entries. These commands form the backbone of everyday interaction with Linux files and directories, whether for managing your own data or analyzing target systems. Beyond file manipulation, cybersecurity often involves monitoring processes, network connections, and system resources. These commands give you insight into what the system is doing and how it's communicating. 1. PS, process status displays information about currently running processes. PSAUX is a common combination that shows all processes, A, including those of other users, U, and processes not attached to a terminal, X. This is essential for identifying suspicious processes running on a system, which could indicate malware or unauthorized activity. 2. Top provides a real-time, dynamic view of running processes, CPU usage, memory usage, and more. It's like a live dashboard for your system's activity. Security analysts often use Top to identify processes consuming excessive resources, which could be a sign of a denial-of-service attack or a cryptomining malware. 3. Netstat or SS, network statistics. These commands display network connections, routing tables, interface statistics, and more. Netstat, TOMP, or SS, TOMP, is a very common flag combination, T, TCP connections U, UDP connections L, listening sockets N, numeric addresses, don't resolve hostnames, P, show the process ID and program name. This command is vital for discovering open ports, active network connections, and which processes are responsible for them. Critical information for both attackers looking for entry points and defenders monitoring for unauthorized communication. 4. Ping, used to test connectivity to another host on a network. Ping Google.com sends ICMP echo requests to Google servers and reports if they respond, indicating network reachability. It's a basic but fundamental network troubleshooting tool. 5. Ifconfig or IPA, interface configuration/IP address. These commands display network interface information. Ifconfig, older but still common, or IPA, newer, preferred on modern systems, shows your IP address, network mask, MAC address, and other details for each network adapter. This is crucial for understanding how your machine is connected to the network and for configuring network settings. These system and network utilities provide a crucial window into the operational state and network behavior of a Linux machine, offering valuable intelligence for both offense and defense in cybersecurity. One of the most fundamental aspects of understanding Linux, especially from a security perspective, is its file system hierarchy. Unlike Windows, which uses drive letters like C and D, Linux organizes everything under a single, unified tree structure starting from the root directory, denoted by a // This structure is standardized by the File System Hierarchy Standard, or FHS, which dictates the purpose of each primary directory. Knowing this structure is vital for navigating systems, finding configuration files, locating logs, and understanding where applications store their data. Let's look at some critical directories / root. The top-level directory. Everything else branches off from here. /bin and /usr/bin contain essential user commands, executables, that all users might need, like ls, cp, mv, /usr/bin holds non-essential user commands, /spin and /usr/spin, store essential system binaries, often for system administration, like reboot, disk. These usually require root privileges, /usr/spin holds non-essential system binaries, /etc. This is a crucial directory for cybersecurity. It contains system-wide configuration files for almost all services and applications. Examples include password, user accounts, shadow, hashed passwords, sudoers, sudo permissions, and configuration files for web servers or SSH. Compromising /etc. can be devastating. /home contains the home directories for regular users. Each user typically has their own directory here, e.g., /home/Kali. This is where users store their personal files, documents, and user-specific configurations, /var, short for variable data. This directory contains files whose contents are expected to change frequently during normal system operation. Most importantly for cybersecurity, it's where log files are stored, e.g., /var/log, which are critical for forensic analysis and intrusion detection. Other data here includes mail queues, printer queues, and temporary web files. /TMP contains temporary files, often created by applications. Files here are usually deleted upon reboot. Attackers sometimes use /TMP to drop their tools or exploit temporary file creation vulnerabilities. /opt, used for installing optional software packages that are not part of the default distribution, often third-party applications. /USR, pronounced user, but stands for Unix System Resources. Contains executables, libraries, documentation, and source code for most system utilities and user applications. Understanding this layout is like knowing the floor plan of a building. It tells you exactly where to look for specific information or potential vulnerabilities. One of Linux's most robust security features, and a critical concept for cybersecurity, is its file permission system. Permissions control who can do what with a file or directory. They are fundamental to preventing unauthorized access, modification, or execution of sensitive data and programs. Every file and directory in Linux has three types of permissions for three categories of users. 1. User, owner, the person who owns the file or directory. 2. Group, a collection of users who share specific permissions. 3. Others, everyone else on the system. For each of these three categories, there are three types of permissions. Read allows viewing the contents of a file or listing the contents of a directory. Write allows modifying, deleting, or renaming a file, or creating/deleting files within a directory. Execute allows running a file as a program or script, or entering a directory. These permissions are often represented in a string like rwxrxr, or, more commonly in cybersecurity, using octal notation. R equals 4, W equals 2, X equals 1, no permission, equals 0, so, RWX is 4 plus 2 plus 1 is equal to 7, RW is 4 plus 2 plus 0 is equal to 6, RX is 4 plus 0 plus 1 is equal to 5. A common permission 755 means, owner, RWX, 7, read, write, execute group, RX, 5, read, execute others, RX, 5, read, execute. To change permissions, you use the chmod command. For example, chmod 755 script.sh would give the owner full permissions, and group/others read and execute. To change the owner of a file, you use chown. Chown user1 file.txt makes user1 the owner. To change the group ownership, you use chgrp. chgrp devteam file.txt assigns devteam as the group. Think of it like a house, the owner has keys to everything, RWX. Family members, group, might have keys to some rooms, RX, and visitors, others, might only be allowed in the living room, R. Misconfigured permissions are a common vulnerability. For example, a sensitive file with RWRWRW permissions means anyone can read or write to it, which is a major security flaw. Understanding and correctly managing these permissions is a cornerstone of securing any Linux system. Managing software on a Linux system is vastly different, and arguably more efficient, than on Windows or Mac OS. Instead of manually downloading installers from various websites, Linux distributions use package managers. These are sophisticated tools that automate the process of installing, upgrading, configuring, and removing software packages from centralized repositories. This approach provides significant security benefits, as packages are typically verified and digitally signed, reducing the risk of installing malicious software. For cybersecurity professionals, package managers are essential for setting up their toolkits, keeping systems patched, and installing dependencies. Let's look at the two most prevalent package management systems. 1. APT, Advanced Package Tool. This is the package manager used by Debian-based distributions, which includes incredibly popular distros like Ubuntu, Kali Linux, and Parrot OS. Sudo apt update. This command updates the list of available packages from the repositories. It doesn't install anything, just refreshes the database of what's out there. You should always run this before installing new software or upgrading. Sudo apt upgrade. This command installs the newest versions of all currently installed packages. This is crucial for applying security patches and keeping your system up to date against known vulnerabilities. Sudo apt install package_name. This installs a new package and all its necessary dependencies. For example, sudo apt install map would install the map network scanner. Sudo apt remove package_name. This uninstalls a package, but usually leaves behind configuration files. Sudo apt purge package_name. This uninstalls a package and removes its configuration files, for a cleaner uninstall. Sudo apt auto remove. Removes packages that were automatically installed to satisfy dependencies for other packages and are no longer needed. 2. Yum, Yellow Dog Updater, Modified, /DNF, Dandified Yum. These are the package managers used by Red Hat-based distributions, such as Fedora, CentOS, and RHEL. DNF is the newer, improved version of Yum and is now standard in most modern Red Hat derivatives. The commands are very similar. Sudo yum update or sudo dnf update, updates the local package index and then upgrades all installed packages to their latest versions, including security updates. Sudo yum install package_name or sudo dnf install package_name, installs a new package and its dependencies. Sudo yum remove package_name or sudo dnf remove package_name, removes a package. Understanding and effectively using package managers is a cornerstone of maintaining secure and functional Linux systems, whether you're building a penetration testing lab or managing production servers. They ensure you're working with the latest, most secure versions of your software. Let's bring these concepts to life with a couple of real-world cybersecurity scenarios where Linux shines. Scenario 1, the ethical hacker's reconnaissance. Imagine you're an ethical hacker, performing a penetration test against a client's network. You boot up your Kali Linux machine. 1. First, you need to understand the network layout. You'd use ifconfig or IPA to check your own network interface, then ping to verify connectivity to target systems. 2. Next, you'd launch Nmap, a powerful network scanner often pre-installed on Kali. You might use Nmap, SVO target_IP to identify open ports, services running on those ports, and even guess the operating system. Nmap itself is a Linux application, and its output is often piped through other Linux commands. 3. If Nmap reveals an open web server, you might then navigate to its configuration files using cd/etc/apache2, if it's Apache, and ls/l to inspect permissions, or cat and grep to search for interesting settings in log files within /var/log/apache2. 4. Should you find a potential vulnerability, you might then utilize a framework like Metasploit, another Linux native tool, to attempt an exploit. The entire workflow, from discovery to exploitation, is driven by Linux commands and tools. Scenario 2, the security administrator's defense. Now, let's switch to the defender's perspective. You're a security administrator monitoring an Ubuntu server for suspicious activity. 1. You receive an alert about unusual network traffic. Your first step might be to log into the server via SSH, a Linux service, and run netstat, tomp or ss, tomp to identify any unauthorized listening ports or outbound connections, checking which processes are responsible with the process ID information. 2. If you suspect a brute force attack on SSH, you'd immediately examine the authentication logs. You'd navigate to /var/log/auth.log and use grep, failed password 4, to quickly filter and identify patterns of failed login attempts, potentially blocking the attacking IP address with firewall rules. 3. To ensure the server is protected against the latest threats, you regularly run sudo apt update followed by sudo apt upgrade to apply all available security patches and software updates. This keeps vulnerabilities at bay by ensuring all software components are up to date. In both these scenarios, Linux's command line power, robust file system, and integrated security tools are not just helpful, they are absolutely essential for effective cybersecurity operations. To further solidify our understanding, let's consider a classic case study of how Linux vulnerabilities are exploited and how our knowledge of Linux fundamentals helps us both exploit and defend. Many significant cybersecurity incidents have leveraged vulnerabilities in Linux systems or software running on Linux. Consider the Dirty Cow vulnerability, CVE 2016-5195. This was a critical Linux kernel privilege escalation vulnerability that allowed a local attacker to gain root privileges on the system. It was present in virtually all Linux distributions for many years before it was discovered and patched. How it was exploited: an attacker who had already gained low-level access to a Linux machine, perhaps through a weak password or a web application flaw, could use the Dirty Cow exploit. This exploit leveraged a race condition in the kernel's memory management to write to read-only memory mappings, essentially allowing them to modify files they shouldn't have access to, for example, the /etc/password file. By modifying this file, an attacker could create a new root user or change the password of an existing root user, thereby gaining complete control of the system. Our Linux knowledge in action, understanding file system and permissions. The core of Dirty Cow was bypassing file permissions, RWRR, for /etc/password, to modify a critical system file. A defender, understanding these permissions, would know the severity of such a bypass. Essential commands: an attacker would likely use cat /etc/password to view the file before and after modification, Huami to check their current privileges, and various compilation commands to build the exploit code, often downloaded to /tmp and then executed. A defender might use PSAUX and TOP to identify unusual processes or resource spikes associated with the exploit running. Package management: the ultimate defense against Dirty Cow was patching the Linux kernel. A system administrator with knowledge of apt upgrade or DNF update could quickly apply the necessary security updates across their fleet of Linux servers, closing the vulnerability window. Failure to do so would leave systems open to exploitation. This case study vividly illustrates that understanding the Linux file system, permissions, command line operations, and package management isn't just theoretical knowledge, it's the practical foundation for both identifying and mitigating real-world cybersecurity threats. We've covered a significant amount of ground today, laying the critical foundation for your journey in cybersecurity with Linux. Let's quickly recap the key takeaways from this intensive episode. First, we solidified why Linux is essential for cybersecurity, emphasizing its open-source nature, unparalleled flexibility, stability, vast array of specialized tools, and the power of its command line interface. These attributes make it the platform of choice for both offensive and defensive security operations. We then explored key Linux distributions like Kali Linux and Parrot OS, which are purpose-built for penetration testing and forensics, as well as Ubuntu, a general-purpose distribution widely used in server environments and highly customizable for security tasks. The bulk of our practical learning focused on essential Linux commands. We covered how to navigate the file system with pwd, ls, and cd, manipulate files and directories with mkdir, cp, mv, rm, cat, and less, search for patterns with grep, and monitor system and network activity with ps, top, netstat/ss, ping, and ifconfig/ip. Mastering these commands is your first step to proficiency. We demystified the Linux File System Hierarchy Standard, FHS, explaining the purpose of critical directories like /etc, /home, /var/log, and /tmp. Understanding this structure is paramount for locating configuration files, logs, and potential areas of interest or vulnerability. Crucially, we delved into file permissions, learning about RWX and octal notation, and how chmod, chown, and chgrp are used to control access. We highlighted how misconfigured permissions are a common security flaw that attackers frequently exploit. Finally, we learned about package management with apt for Debian-based systems and yum/dnf for Red Hat-based systems. These tools are vital for securely installing software, maintaining dependencies, and most importantly, keeping your systems patched against the latest vulnerabilities. Remember, practice is key. The more you interact with a Linux terminal, the more intuitive these commands and concepts will become. This is just the beginning of your Linux journey in cybersecurity, but it's a powerful start. You've just taken a monumental step in your cybersecurity education by embracing the fundamentals of Linux. The skills you've acquired today will serve as a bedrock for almost every advanced topic we cover in this course. But our exploration of operating system security is far from over. While Linux is dominant in many cybersecurity contexts, another operating system holds an equally significant, though different, place in the digital world: Windows. In Episode 7, we'll shift our focus to Windows operating system security. We'll explore its architecture, understand common vulnerabilities, delve into Windows-specific security features like group policy and the registry, and discuss essential tools and techniques for securing and analyzing Windows environments from a cybersecurity perspective. It's an entirely different beast with its own set of challenges and defensive strategies, making it another indispensable skill set for any security professional. Don't miss out on the next crucial installment. If you found this episode helpful and want to continue building your expertise, please take a moment to like this video, subscribe to our channel for more in-depth cybersecurity content, and hit that notification bell so you don't miss future episodes. Your engagement truly helps us grow this course and reach more aspiring professionals like you. Feel free to leave a comment below with any questions, insights, or topics you'd like us to cover. And of course, share this course with anyone you think would benefit from this structured cybersecurity education. Thank you for being a part of this learning journey. Stay curious, stay secure, and I'll see you in Episode 7.